Good morning, everyone. Welcome to Combustion webinar, and I am Peng Zhao from the University of Tennessee. It's my great pleasure to introduce you our speaker today, Professor Xinyu Zhao, who is a centennial term associate professor at the University of Connecticut. She joined the School of Mechanical, Aerospace, and Manufacturing in spring 2015 as an assistant professor, and then before that, she was a postdoc research fellow in CEFRC at Princeton, co-sponsored by Sandia and Penn State. She received her PhD degree in mechanical engineering from Penn State in 2013, and she received her bachelor's and master's degree in thermal engineering from Tsinghua in 2006 and 2008, respectively. Professor Zhao's research program is supported by NSF, ACS, NASA, AFOSR, and ONR. She has also been actively working with industrial partners as FM Global and Raytheon Technologies Research Center. Professor Zhao is a recipient of a few prestigious awards, including the AFOSR YIP Award, NSF Career Award, and Combustion Institute's Irvin Glassman Young Investigator Award. Her research interest includes detailed radiation modeling for multi-phase combustion systems, turbulent combustion modeling, detonation, and interplay between experiments and computation, as well as high-performance computing. And today we have Professor Zhao talking about recent progress of radiation modeling in combustion. And thank you very much for your time, and the time and the podium is yours.
Thank you, Peng, for your introduction, and also thank you for the organizing committee to invite me here today. Today, I'm going to share some of our recent work regarding radiation, and in particular, we want to talk about radiation in combustion. So first, I want to provide some perspective about where radiation is with respect to the rest of the combustion community, since this is a combustion webinar. In recent years, with increasing computational resources, combustion research has been has advanced to include more multi-physical effects with increasing accuracy. Depending on what you want to study, we might put more emphasis or higher resolution, higher accuracy models in different aspects. So I'm showing a few examples in terms of our research. We try to study the black body stabilized flame blow-off phenomenon. And we also, in a related subject, we try to study the flame kernel extinction. So for these topics, we hope to understand turbulence chemistry interactions. So there, we would rather spend the additional computing power on better turbulence model. So that's why this first item I'm saying is we have seen increasing studies goes from RANS to more LES, and now even a lot more DNS studies nowadays. Again, depending on what the goal is, you can also go to the other extreme and study a large-scale combustion phenomenon. Here I'm showing one of our simulation of a small pool fire, which is actually experiments were from Professor Jay Gore's group many years ago. So there, the goal again is to understand the radiation behavior. But to do that, we have to have very accurate fluid flow simulations, and we have to account for the effect of soot. And with all that, we chose to do a very accurate simulations. So as you can see, basically there are many areas that are critical for a combustion simulation to be successful. There's the fluid flow, there's chemistry. We have seen more chemistry going towards detailed or reduced chemistry rather than global chemistry. We have seen more complex turbulence chemistry interaction models. We have also seen more multi-physics. So a lot of research has been dedicated to spray, coal, or soot because they are very relevant to practical devices. And we also seen a lot of the simulations go larger scale. So with this as the context, it seems we never will have enough computing resources. So it's always a trade-off what to simulate. among all of these, radiation is really just a very small area. So it's not surprising that it has a relatively small community to study radiation in combustion. So when is radiation important in terms of in the context of combustion, right? So first, I would say when radiant fraction is significant. So radiant fraction means how much the radiation loss is with respect to the total heat release. So I'm showing one example on the right. I hope you can see my cursor. So this is one of the, again, the simulation of the small pool fire. And the pool fire was a 4 kilowatts power pool fire. That means the heat release rate is 4 kilowatts. And the radiation loss there is about 1.2 kilowatts, which is about 30%. So this 30% number is radiant fraction. So when this number becomes significant to your application, you want to consider radiation, right? We further break down that radiation loss into two parts that always exist. One is the emission, and then is the reabsorption. So when radiation leaves the spot, it will get reabsorbed in the neighboring spots. So that's the absorption means. So you can see emission is larger than absorption, and emission minus absorption would be the total radiation loss. Okay. Another scenario where radiation would be important in combustion would be when we are trying to predict temperature-sensitive pollutants, such as NOx, soot, CO, anything that has a slower chemistry that depends on temperature. We should consider radiation to get the temperature more accurate. Another scenario will be when predicting limit behaviors. So I'm showing another example on the right where we implemented a new radiation model into Flame Master, where we are trying to look at extinction limit. And as you can see on the left is this slow, small extinction strain rate limit. And at that stage, flame is thick, so the loss becomes more important with respect to the heat release rate. And as you can see, the red curve is without considering radiation, and we totally miss the extinction limit prediction. And when you do consider radiation, I'm showing 3 different types of models, and you can see that the model difference actually can be told here. They have different results in terms of the limit prediction. And lastly, I think when someone is concerned about wall heat transfer radiation, and when that device has significant radiation, people should pay more attention to radiation. So as you can see, not every combustion application actually needs radiation. So that's another reason I think radiation modeling in terms of in the combustion community is not a very big topic. And I think it's reasonably so. All right, so now this talk, I think I will just focus on the problems where radiation do play a role. And I want to share what we have learned in modeling radiation in combustion in the past 10 years, I would say. And I want to share some recent progress on a GPU-accelerated radiation solver and provide my vision for what can happen in 10 years. All right, so we will go through the first section first. Want to talk about radiation heat transfer. I'm showing one diagram here. I will explain more. So, all right, so I think first I want to review the basics. I guess if anyone has taken any heat transfer class, if you remember only one thing about radiation, that would be radiation has a dependence on temperature as T to the 4th, right? So more accurately for a medium that is participating, for example, combustion, right? We have CO2, we have water, we have soot, we have CO, all of these are emitting radiation. So for these kind of participating medium, its absorption coefficient also matters. So it's the product of the two. But I want to focus on the T to the 4th a little bit. It's very simple function to understand, but I want to offer the right graph. If you take a look at the right graph, it's a plot of t to the fourth normalized by 1,000 to the fourth. What I'm trying to show here is if you look at the ratio, so if you look at the temperature of 1400 K, that's about the average temperature of pool fire. And you can see that the T to the fourth is about 4 times the amount of 1,000 to the fourth, right? 1,000 would be a relatively lower temperature of that region. Another limit would be at higher temperature. So, we have other applications where temperature can go easily 2,000 Kelvin. And if you look at there, the 2,000 Kelvin versus 1,400 Kelvin, the ratio will be another fourfold, right? So this is important because it indicates where radiation emission is most significant. So if you look at the example on the left, what I'm trying to show here is a simulated laminar diffusion flame. And you can see, as expected, right, we have high temperature here near the stoichiometric line, and that temperature reaches around 1900. So this is methane, around 1900 Kelvin to 2000 Kelvin, depending on whether radiation is included. And on the second one is the kappa term, the absorption coefficient. So we are looking at a value, say around 1. So the yellowish is 1, and around the red part is about 1.2. So I would say throughout the flame for this laminar flame, kappa is relatively constant. So the major term would be the T to the fourth in terms of emission. So that's why when you see the actual emission source term from radiation, it follows the profile of temperature. Okay, if you look at a cross-section of the flame, so that shows you the thickness. So basically that layer of high temperature above, I would say above 1400 K, where we just talked about, it's only about 5 millimeter. And this is a laminar flame, and you can imagine for turbulent flames, the flame surfaces can be even thinner. And although we will have a lot more surface area for those kind of flames, but the first observation doing a lot of combustion simulation is high temperature zones are relatively confined. Okay. Now, a second law in radiation that is very relevant is called Beer-Lambert law, and it describes how much radiation is absorbed after passing through a medium that is participating or absorbing. So the simple description of that law is the exit intensity of radiation divided by the entering intensity is decaying exponentially as a function of optical thickness. So now optical thickness is a non-dimensional quantity. It is the product of the absorption coefficient, which is determined by the mixture, and also the product of that with distance. So in terms of combustion, that means a characteristic length scale. Okay, so I'm offering a few numbers here, as you can see. So if this optical thickness is 0.1, you see about 90% of the energy will exit from the other side. So 10% gets absorbed, right? If the value is 2.3, so only about 10% leaves. And if the value is 4.605, you actually get only 1% leaving the medium. So I think this offers everybody a reference when we talk about optical thickness. So oftentimes, as a new student entering the field, you probably hear, okay, if this flame is optically thin, you can use this model and that, right? So how do you define optical thin or thick? So I think these numbers from the exponential function will be helpful. A second thing we can learn from the math here is I'm drawing that exponentially decay function here. And as you can see, I'm putting this green bar. Each of them has the same thickness of 0.4. So 0.4 of optical thickness is pretty typical of a value from a laminar flame, right? And what you can see here, if you see the difference, so that will tells you the how much gets absorbed basically by that medium. And you can see if you follow the history of one ray, the amount that getting absorbed by the medium is increasingly smaller when the ray keeps if you're tracking that radiation ray over the medium. So what does that mean? That means actually absorption immediately to the emission point is the most significant. It does get increasingly smaller and smaller. The ray has less to offer to far away field, although it does have energy to be deposited into the far away field. We have often talked about radiation being a non-local phenomenon, right? So at one point you have a bonfire. If you stand far away from it, you can still feel the warmness of it, right? So here I want to emphasize that it does decay how much energy it can deposit over the same optical thickness. To summarize what I just mentioned, so the T to the force dependence, it actually tells you absorption is more significantly impacted by the high temperature flame surfaces than by the low temperature regions of the flame. So that means if you can only capture one thing, you probably want to capture the high temperature flame surface. The second Beer-Lambert law tells you a closer source has a much stronger impact on you, right? As I mentioned, the most amount of energy actually got deposited when the ray just got emitted. So if a source is closer to the point you care about, it actually has more impact on it. And that number of 4.76, basically anything beyond that has no impact on the current point you are looking at. So based on these two observations, we actually proposed a model to verify these concepts and also as a model for radiation. So the model does one interesting thing. So for example, we have a asymmetric, axisymmetric laminar flames here. And what we did is we map the temperature. So you can think of this as a flamelet concept. We map that the temperature, species, and all the other radiation relevant quantity profile to a cylinder. And this cylinder is basically one-dimensional. It is infinitely long in this axial direction, and it only varies in the radial direction. This basically captures what I just summarized, right? We captured the high temperature zone. We made it one infinitely long because beyond 4.76, nothing matters. So that doesn't pose any issues. However, once we make it infinitely long and we make it 1D, we can find an analytical solution. And by doing that, on the right-hand side, we are actually comparing results from our cylinder representation of a flame to the flame solution itself in the symbol. And as you can see, so the net radiation loss is predicted pretty well. Radiation absorption, which is the more difficult part to predict, we have also very good agreement. So that means the concept we just talked about actually works. And this model actually has been implemented into Flame Master to assist our one of the simulations we are trying to do right now. All right, so with that as the basic characteristics of radiation in combustion, I want to talk a little bit more on the modeling, right? So what I'm showing here is the so-called radiative transfer equation that is solved essentially when you try to solve a radiation model. And it is a steady state equation, as you don't see any time term because radiation travels at speed of light. It is much faster compared to our combustion system. It won't be the case if you're talking about combusting supernova, right? All right, so now if you look at here, we have a few terms. You have emission term. So this is determined purely by a local property, composition and temperature. And then you have the absorption term. And then you have a outscattering term. So any scattering particles, droplets, they will change the ray from its current direction to some other direction. And we consider that as a loss. And lastly, we have an in-scattering term, which basically scatters radiation from other locations into the propagating direction of S. So if you add them all together, that should describe the intensity change of radiation. All right, so to solve this equation, we need a few things. First, we need all these kappa and sigma. So these are properties, and they oftentimes depend on the wavelengths. So there are a hierarchy of models describing that. In the scattering term, if you do have scattering medium in your system, there's a phase function there, and you have to somehow give that phase function. And now, once you have all the properties, you still have to solve this equation. And it's a differential integral equation, which is not that easy to solve. So there are all kinds of solvers invented. People might have heard P1, probably have heard DOM. These are implemented in ANSYS Fluent and many other softwares. And the most accurate one would be a Monte Carlo solver. As I already mentioned, the names of these solver, P1 usually considered to be relatively cheap, very easy to implement, and however, it might have large errors for many conditions. Discrete ordinance method probably is the most popular model that if you want to balance cost and easy of implementation and also accuracy. Lastly, the most complicated one will be the Monte Carlo solver. It's very expensive. It's very rare in CFD packages. I think ANSYS start to have it, but it's often used to get benchmark solution to also verify other solvers. I'm showing one example here, which is our collaboration with Jackie on simulating a backward-facing combustor. And so here we look at radiation, and we tried different models. FVM is another kind of a finite volume radiation solver, similar to DOM. We have the P1 solver, have Monte Carlo solver with different numbers of arrays and different numbers of repeated runs. So as you can see, FVM, this finite volume method, it actually does a fairly good job. Monte Carlo solver, you can see it's a signature noise, but the noise can be reduced if you run multiple times, which also increases the cost, right? So that's just a typical examples of these solvers. Now, if you do have droplets in your system, so I'm showing a canonical box simulation where we did with FM Global. We injected droplets, water droplets into the system, and we want to see the prediction of radiation. And what I'm showing here is a few different solvers. Again, we considered MCRT, which is the Monte Carlo solver, as the benchmark. And here just shows using different solver with property combination, you can get very different results. More importantly, I want to highlight that here it shows the cost. So for the discrete ordinance method or the finite volume method in general, you have to divide the solid angle into sub domains. And you can see the cost actually increasing very fast when it passes certain range. So for this particular example, the right-hand side shows the cost, and the best balance actually between cost and accuracy would be around 256 sections of the solid angle. And you do improve your accuracy more. However, the cost is significantly more with if you go to 1024. I mentioned spectral behavior a few times already. So this talks about the mixture absorption coefficient is highly intermittent. As you can see, I'm showing examples of CO2, which is one of the major species for emitting radiation in combustion. And at a lower pressure, you can see all these lines. They are very intermittent. Radiation has strong absorption coefficient and a few discrete wave numbers. When pressure increases, so for example, this line, you can see the line actually got smoothed out a lot. That also actually implies modeling gets simpler when you have higher pressure. The absorption coefficient is also a function of temperature. So what I'm showing here is some sort of averaged absorption coefficient. We call it Planck mean absorption coefficient. And as you can see, for different species, they are a function of temperature, and actually they have relatively lower values at higher temperature and higher values at lower temperatures. And soot also depends on temperature, but not as significantly as what you can see from the gas species. To describe these behaviors, I mentioned there are a hierarchy of models ranging from simple weighted sum of gray gas models. Oftentimes you require case-dependent tuning. If you look at conventional air combustion versus oxy combustion, you need different coefficients. There's narrow band models, there are wide band models. I'm showing here is one very elegant work from Professor Dan Harris' group on using a band model to simulate IC engine. So as I mentioned, when pressure is high, actually the spectral behavior is less intermittent. That makes the modeling wide band models more suitable for that situation. And you can use a fraction of the cost of the most expensive model to get almost similar results within 10% of the error. And then lastly, the most accurate model still considered to be the line by line model that describes every line you saw on the previous page. In terms of soot, we oftentimes consider soot to be small enough. So we use the Rayleigh scattering limit, and we use this formula here to compute its absorption coefficient as a function of its volume fraction. So as you can see, if you want to predict soot irradiation correctly, you have to have the soot volume fraction correctly in this case. So then you still have to have the complex index for soot, refraction index for soot, and these are from curve fit, maybe say 30 years ago. There are recent development on this end too. So I hope we have some updated values for soot radiation in the near future. And if we have larger particles than soot, so droplets, and sometimes if you're looking at solar heaters where they have aluminum particles or nanoparticles, other type of particles in them, you might have to consider if the diameter is comparable to the wavelengths you are interested in, you probably have to do Mie theory of that, which is very complex in terms of its mathematical representation and in terms of cost. So we did this with water droplets a while ago. So eventually to compromise between cost and accuracy, we have to tabulate the Mie expression essentially, and has a truncation at certain terms. But as you can see, the modeling of such system can be very complex. What I'm showing you here is the two components, the real index N and the imaginary index of K for droplets, for water droplets. And you can see its absorption coefficient varies significantly with wavelengths. Another factor with water is described by this asymmetry factor G. So if it's 0, it means it's isotropic scattering, which is relatively easier to model. But unfortunately for water, it is around this range. So it's heavily forward scattering. So that's where we see if you use a wrong model, you get better results actually from not using any model. So it can be confusing in radiation calculation because sometimes really with a model you are doing worse. So anyway, as you can see, it's very complex and it seems the cost is high. So I just want to offer my vision here after working on this for many years. That is, I think radiation modeling can be solved. I will say 95% of the problems can be solved relatively cheap in a decade's time. And I propose to use the method of the line by line spectral database, and you can consider using the Monte Carlo solver. And this may sound counterintuitive because I'm picking really the most expensive radiation solvers available. But I hope I use some other examples to show, first, it's worthwhile to do that. Two, it's possible to do that. So let's first talk about see a few examples. I'm offering two examples, and I want to talk different aspect from the two. First, it's a series of laminar flames. They have a different mass flow rate. So 2 different flames. This is also a video, so it's a steady laminar flame. When you crank up the mass flow rate, you see flickering from this flame. So this is a collaborative effort back in 2019. I think we want to have a model validation workshop for radiation. So this is one of the configuration there. So our idea was, let's use the best possible models we have, and so that we can get the best solution for radiation for this case. And let's compare 2 experiments to see what we are missing. And we did a axisymmetric mesh. We considered the gravity. We considered the nozzle because the preheat can be significant. We used skeletal mechanisms, 2 of them, because later we realized we need soot. Probably our soot model is the most weakest link in all these modeling approach, but for a Centauro type of burner, the 2 equation model should be sufficient. And radiation, we use the Monte Carlo solver with the lemma line database. So first round, I want to show some results. We tried applying these solvers directly to the flame. And we don't want to change anything. So we apply the same models to both flames, a smaller one and a bigger one. And what's interesting is this, as in both cases, we saw that the adiabatic nozzle has a better prediction than the non-adiabatic nozzle. And we know in experiments, there's no insulation. So we know that the non-adiabatic one should be the more realistic one or physical one, right? So this doesn't make too much sense. Well, since we do have fair confidence in the radiation model, we didn't stop there and point a finger to say maybe it's the radiation model that is not making sense here. So we think it must be something else. And that something else is we look at the flame and realize it's pretty yellow, and we talk to the experimental partner and they confirmed there is soot actually, it's just they didn't measure it. So now with that information, we go in and then throw the 2 equation model of soot in and then do everything again. So this is for the bigger flame I'm trying to show here. As you can see, these curves, they are all from, so they are using different chemistry models. They are using different radiation models, but you don't see much difference from all of them. And they are all under predicting the radiative heat flux from the side of the flame. Now, once we have soot considered, you can see the curves actually is going into the same levels of experiments, and it's filling the error bar. So that's all good news. The 2 different lines here, the green versus the cyan color here, they are, one of them is with optically thin model, one is with the Monte Carlo with reabsorption. So there is a difference, but I wouldn't call that difference significant for this case. So what do we learn from this exercise? This exercise actually told us, also confirms a lot of the practice in combustion is optically thin model for small laminar laboratory flame is probably sufficiently accurate. So basically using that big radiation model has no impact, not too much impact on the results we get. However, it does have an impact psychologically, I would say, because we are trying to understand this flame without any previous simulation or guidance or anything. We have this experimental image that's all it is. And it is important at that situation to have a trustworthy radiation model, so we don't wrongly, think it must be the radiation model that makes the results wrong. Instead, because of the trust, our confidence in the radiation model, we are able to, go to the direction that leads us to the final answer to the question. So that's the first lesson we learned from that exercise. I still just recommend optically thin to many people if they don't want to bother to put a radiation solver in their code, and I think that's sufficient. You also see the challenge from this example. That is, if you just want to get radiation correct, in combustion, you have to get a lot more correct before that. You have to have the flow field correct. In this case, for these flickering flames, you have to get a puffing frequency right. That means you have to have enough resolution, you have the molecular transport figured out, and you have to have soot in that case. And soot, I would say, is probably the most difficult, the problem to crack in radiation, in combustion. And then the thermal boundaries from the nozzle and other chemistry and all of that can play a role. So that's why I think it's difficult to judge a radiation solver in combustion, because there are so many other things that are purely combustion that can be wrong. So that's from that, you know, we like what we learned there, and then we carry that knowledge to the next simulation, which is a small scale pool fire. I would say it's fairly laminar in the base. So this is experimental image, and this is what we got from simulation using similar technique. And they look fairly similar, I would say, from a qualitative point of view. Before I talk more about the modeling, I just want to say the standard practice nowadays in, I'll say, academia, modeling pool fire is for turbulence. A lot of us use LES, and combustion is a diverse selection of models. But for industrial applications, a lot of them still just use a fixed radiant fraction. Basically, you take off 30% of energy from your energy equation and call that radiation and be done with it. We do see more detailed models recently because the need of understanding really how radiation works in fire, because you want to have different suppression strategies and radiation loss, as I mentioned many slides ago, at that low strain rate extinction limit, it will play a role. So with that, we thought, okay, let's try to get as fine resolution as possible with this flame, since we want to, again, remove uncertainties from other models. And so we have about 10 million cell mesh that probably resolve the Kolmogorov scale, depending on how you define it. And it's about 7 grades across the flame thickness and about 4 across the soot layer. And we used mixture averaged molecular diffusion model. We used finite rate chemistry, 2-equation soot model. And with that, there are a few things to compare from the experiments. Puffing frequency, it's fairly well, and that is easy to capture for most of the simulations, as long as the LES resolution is enough. Radiant fractions, we got fluctuating ones. They seem to reach the experimental value. And also, you can see from here, we did try simulation without any soot, and the prediction is very low. So yeah, and this experiments did report soot. So we then turn on soot model. You can see it bump up the level even higher. Recognizing this is a log scale on the left, I just want to say there's still uncertainties there with the soot prediction in our simulation. And we did a little sensitivity analysis on the right. So basically, change the soot volume fraction by 50% up and down, and you can see that can change the results basically above and below the so within the error bars of the experiments. So with these, we think we have a fairly good capture of what the flame is like. And so we go ahead to learn more about the flame. So with the Monte Carlo radiation solver and the Lambda line database, we can get a lot more information. For example, you can see on the left and right are the emission and absorption spectrum we collect from the entire domain. So it shows a few signatures here. So we can collect from different species and different location. And here you can see a peak. So again, this is a log scale, a peak emission wavelength around 4,300 nanometer. That is a CO2 peak. The secondary peak would be around here, which is about 2,700. And that is both CO2 and water contributes to that. And you see some even smaller peaks from the gas phase. Now there's this continuous curve, which is soot. So we all know that soot has broadband behavior. So this is example of that. So it has a continuous value throughout the entire wavelengths we are looking at. And it is comparable to this 2,700 nanometer band strength. It's relatively smaller compared to CO2. Now, this is what has been absorbed, right? So this is, we collect radiation that is on the boundary. So that is after emission being absorbed within the medium, and you see its distribution. So we still see the same signature, right? So CO2 is still here, although its magnitude is reduced a lot compared to the left phase. So that means there's quite some self-absorption of CO2. This peak actually doesn't change that much, which is an interesting observation, and I might talk more about that later. And the only thing you see, the soot also has almost unchanged curve, except within this very strong CO2 band, it got a little dent here. So essentially, that's the level of interactions of soot radiation with the rest of the medium. It's only at a few discrete wavelengths. So to make this more concrete, we show more statistics here on this page. So this shows the emission term that comes out from soot and comes out from the gas as a function of temperature. So you can see at a high temperature zone, it's mostly soot radiation. Lower temperature zone, you have a lot from the gas. And absorption-wise, you can see now a lot of the radiation gets absorbed by the gas, not really, well, that much by soot. So in terms of number, 86% of the radiation emission from the gas is reabsorbed by the gas. And about 8% of the radiation from soot is reabsorbed by soot. The interaction between them is really minimum. So only about 2% of the soot radiation is absorbed by gas, and only about 2% of 3% of the gas radiation is reabsorbed by soot. So why is that? So the spectral behavior is one reason. They don't match exactly in terms of where there is radiation in terms of wavelengths. The flame structure is another reason. So if you look at here, I again showing a cartoon of most likely a diffusion flame. So you can see there is a thick CO2 layer because, so there's a thick CO2 layer. So if you imagine there's radiation from this location at a wavelength of 4,300 nanometer, when it travels, it's very likely to meet other CO2 medium in the domain that also absorbs at the same wavelengths. So there is significant reabsorption because of the relatively thick layers of CO2 gas. On the other hand, for laminar flames and also for this little pulsar flames we're looking at, soot layers are relatively thinner. You don't see a big cloud of soot, shielding the entire fire, but you see them existing in thin layers. And that means when they exit its own emission point, it probably doesn't encounter too much of itself. It only encounters gas phase. And since gas phase doesn't really care a lot of the wavelengths it emits, so it gets, going out of the domain eventually. So I hope that offers a perspective on again, optically thin or optically thick. We often use this term to classify, when we need to use certain model, but I want to say it's probably a lot more complex than that in real combustion systems, especially when you have soot. It can be both optically thin and thick simultaneously. Okay, so with that knowledge, we learn a lot, but you can see we also pay a lot for that. So I'm tabulating the cost of running a post-processing one step. And the method we chose to use is about 370 seconds for that one simulation we run, one step. And optically thin probably takes 1.6 for the entire mesh. This is all counted on one node, one CPU. In reality, we also always run in parallel, so the cost will be smaller than this. But nonetheless, you can see different levels of models. They have a different cost. You can see compared to P1 grade, that's the worst model you probably can have here, it's about 10 times more cost. So it's not that bad actually. If we have to include a radiation solver in the system, it's possible to reduce that tenfold of cost with this most accurate solver, and it's worthwhile the effort. So with that idea, we started to think of different ways of accelerating radiation solver. And this is one of the examples. So I'm just going to quickly go through this. This is still work in progress. So basically, we chose to use the Monte Carlo solver here, and then here I'm showing you a basic procedure of running that solver. So it goes from emitting radiations, we call that ray initialization, from each of the CFD cells, and then we trace each of the rays through their lifetime. To do that, we have to compute the distance. So this is the first step, initialization. And for a Monte Carlo method, we have to generate random numbers, and that determines the emission location, emission direction, and emission wavelengths. And with that, we start the tracking. Tracking, we have to compute optical thickness to use in the Lambert-Beer law. To do that, we have to do some geometrical calculation to see how long is the intersection between the ray and the particular CFD cell. And then we need to retrieve the absorption coefficient for that particular wavelength, and then compute optical thickness, and then do the exponential law, and then keep tracking to the next cell. In terms of determining the absorption coefficient, since it's highly intermittent and we are trying to use the Lambda line database, is a lot involved than just tabulating Planck function. So here, what we do is we leverage previous work from Professor Modest's group and Tao Ren. He is in China right now, I think. So from his work, you can see that we can first choose a emitting species, and then use that information to determine the wavelength. And that whole procedure accelerates this process a lot, and it makes it only about 10% of the overall cost. So the 90% of it is the ray tracing process. It is expensive because we have a lot of rays going through all over the domain. It is also expensive because it's coupled to CFD. We have those underlying CFD cells. And when we run a large simulation, we have to do domain decomposition. So tracing rays across different processors is going to be another challenge. To deal with that, we think of GPUs, because GPUs are fast developing in those recent years from AI and all the other aspects. And it is very friendly for Monte Carlo type of method. You can also call that embarrassingly parallelizable. So in addition to GPU, we also think of to leverage computer graphics algorithms. And one of them is the so-called bounding volume hierarchy. And this package is another open source package from Oak Ridge National Lab. So the basic idea is divide and conquer. And once you form a tree structure in terms of the computing algorithms, you can traverse those tree leaves much faster and get to the location, determine whether that location has a person or not much faster. So this is a structure that helps the distributed ray tracing I talk about when different domain decomposition is involved. So with all of that, we still have to code with GPU, and that is a hard process for any mechanical engineering major. Again, fortunately, I think DOE has done the work for us. They had this COCOS open source portable programming library, and that makes our life much easier. And my student could really just did this within a few months. although to complete the entire code, it takes a little longer, but you don't have to learn CUDA anymore. And everything you need to do is you just have to do a parallel for using Coco's directory, and then you can call different hardwares as you wish. So with that, this is the code we form eventually. It is readily coupled to CFD. So we tried with OpenFOAM. That's the solver we routinely use. And this code is about 3,000 lines of C++, and it's some of our collaborators has already testing this out. I just probably will skip the verification. Conclusion is it looks good. And jump to this final page I want to talk about. So this is, again, we try to compare the cost of the solver compared to a traditional implemented Monte Carlo line-by-line solver. And as you can see here, you can easily switch different hardware here. When we do A100 GPU, which is probably the best moment, you have about 400 speed up compared to just a serial run, right? Now, if you can take that out and compare that with other solver, again, it's not a purely very fair comparison because these cited, but we are just in the situations of something that is more difficult to be accelerated with GPU. In that situation, you can see with GPU acceleration, we can almost get the same speed as P1 solver. That's very promising. That makes us, radiation, everybody in the future probably can run an MCRT line-by-line database and call it a day and without doubting the radiation solver. So I went through the last part very quickly, so I can take any questions if anyone want to, but I just want to repeat, we can see about at least 400 times acceleration, and we also actually have a lot more we are trying to do a lot more that we think can further accelerate the solver. So one thing would be loose coupling. Again, that take advantage of the different time scales in combustion system for chemistry, convection, and also radiation. We can afford to not run radiation every chemistry time step. We can instead run it every 100 chemistry steps, right? And that can be a good saving of time. And with the offloading radiation to GPU, we can also do asynchronized radiation solution, and that might totally hide the cost of radiation in the future. So again, there's a lot more work to do. We haven't really tested too much of the solver in fully transient simulations, and we have to also test this on different hardwares. We did a few, but there are problems to solve there. Okay, so I will stop here, and I want to thank again organizing committee for inviting me today, and funding agency from NSF, FM Global, and ONR to support the majority of the works I'm showing here. And most importantly, the students who worked on the projects, my first PhD, Bifen Wu, my postdoc, Guillermo Fraga, and also my past master student, Nick Tricard. So I will stop here and take any questions. Thank you for listening too.